Okay, friends, we'll see what is QV model analysis in this lecture. In QV model analysis, I have already mentioned in the last lecture that instead of taking the n by n matrix A and decomposing it into model components, here we use reduced Jacobian because we are interested in the eigenvalues and eigenvectors of reduced Jacobian. From the QV sensitivity analysis lecture, you can see that. So the reduced Jacobian equals, the reduced Jacobian matrix is decomposed to theta lambda eta, theta into big lambda into eta, where theta is the right eigenvector matrix and eta is the left eigenvector matrix, and now note that from the definition of right and left eigenvectors, we have A into XR equals lambda R into XR. If this condition is satisfied, then XR is the right eigenvector. So this can be written as A minus lambda R into I whole into XR equals 0. Similarly, for left eigenvector, to define left eigenvector, instead of AX, it becomes XA in the LHS. That's the only difference because we have the same eigenvalue here. For the same eigenvalue, we have both right and left eigenvectors. We have defined it in the last lecture. You can see that. So XL into A equals lambda L into XL, and A transpose minus lambda L into I whole into XL transpose equals 0. Because if we have A and the eigenvalue of A as lambda, the corresponding right eigenvector as XR. Now if we take A transpose, then we will get the corresponding eigenvector as left eigenvector. For right eigenvector, if it corresponds to A, then the left eigenvector will correspond to A transpose. So that is what it is defined here in these two equations. Now let's see JR inverse. Why we are interested in JR inverse or the reduced Jacobian inverse? Because in QV sensitivity analysis, we have seen that delta V equals JR inverse into delta Q. So we are going to write JR inverse in terms of left and right eigenvectors and the eigenvalues by model decomposition. So JR inverse equals theta lambda inverse eta. So here JR was theta lambda eta. Okay, now it is theta lambda inverse eta. Okay, because here we have theta inverse equals eta. Left eigenvector inverse. The right eigenvector inverse equals left eigenvector. This is the property. So we apply it here. So we are getting theta lambda inverse eta for JR inverse. Now we substitute in the QV sensitivity equation for JR inverse as theta lambda inverse eta. So we substitute it here. So we get delta V equals theta lambda inverse eta into delta Q. Now we multiply this equation on both sides by eta. So what we get is eta into delta V. LHS will be eta into delta V, and in RHS we have eta theta into lambda inverse into eta into delta Q. But what is this eta into theta? Eta into theta is identity matrix, right? So this is this we are not writing here. Instead, we are starting with lambda inverse because this is identity matrix. Lambda inverse into eta into delta Q would be, it would be the remaining terms would be lambda inverse into eta into delta Q. Identity matrix is gone. So eta delta V equals, once again I am repeating, eta delta V equals lambda inverse into lambda inverse into eta into delta Q. Okay, now for eta delta V, we write small v, and for eta delta Q, we write small q. So small v equals lambda inverse into small q. Now, this is the vector of modal voltage variations. Small v is the vector of modal voltage variations and small q is the modal reactive power variations. We'll see the relation between modal voltage variation and modal reactive power variations to comment on stability. So here inside the vector v, we have several elements v1, v2, etc. So in general, I am writing it as vi. And inside the vector q, I have q1, q2, etc. So I'm writing it in general as qi, small qi. And inside the big lambda matrix, the eigenvalue diagonal matrix, we have diagonal elements as lambda 1, lambda 2, etc. Okay, if JR is an n-dimensional matrix, then we will have n eigenvalues. So inside this big lambda matrix, we will have lambda 1, lambda 2, etc. up to lambda n. So in general, I am writing here lambda I. And because of this inverse, I am writing it as 1 by lambda I. So small vi equals 1 by lambda I into small qi. Now this is the relation between modal voltage at ith bus. So this I denotes the bus number. Okay, ith bus. If we have n buses, then I equals 1, 2, etc. up to n. Now this is the relation. This equation gives the relation between modal voltage at ith bus and modal reactive power change at ith bus in terms of eigenvalue of the JR matrix. This is eigenvalue of the JR matrix. Now let's see what happens if lambda I is positive. If lambda I is positive, that means for increased reactive power injection at the ith bus, the voltage at ith bus is also increasing, right? They follow the same direction. And in the QV curve, we have seen that the negative slope region corresponds to unstable region and the positive slope region corresponds to stable region. So this corresponds to positive lambda I corresponds to positive slope region, right? Because if we take dV by dQ, that is VQ sensitivity. If VQ sensitivity is positive, that means it follows a stable operating region. Okay, so if lambda I is positive, then it's a stable condition. Now, if lambda I is negative, that means if we are increasing the reactive power injection at the ith bus, still we don't get an enhancement in the voltage profile of ith bus. Rather, we are getting reduced voltage. So it has already become unmanageable, right? Even though we are compensating reactive power, still the voltage is diminishing. Okay, voltage is going down. So this has a negative relation. This has an abnormal relation between Q and V, which corresponds to the negative slope region of the QV curve. So this is an unstable condition. Now, if lambda is 0, what happens? For an infinitesimally small variation in ith bus reactive power injection, the voltage is unmanageable. The change in voltage is it goes unmanageable, right? So it's again an unstable condition. So for lambda I negative, it's unstable condition. For lambda I 0, it's unstable condition. For lambda I positive, it's a stable condition. It's a voltage stable condition basically. Now we'll see this. Dou Vk by dou Qk. This is kth modal voltage sensitivity, QV sensitivity. No, VQ sensitivity. Kth modal VQ sensitivity. Dou Vk by dou Qk, which is equal to sigma I. This is theta Ki into eta Ik whole divided by lambda I. We'll do a problem on this, then you'll get an idea about how these variables are substituted with respect to number of buses and number of modal components. Before that, we'll analyze this equation and we'll move forward. So the VQ sensitivity, kth model VQ sensitivity is dou Vk by dou Qk, which is equal to sigma I theta Ki into eta Ik divided by lambda I, which means this theta corresponds to, what is theta? Right or left? Once again, I'm going to the main equation. Theta is right eigenvector matrix of Jr and eta is the left eigenvector matrix of Jr. So we are representing Jr right and left eigenvectors whole divided by the eigenvalue, and the sign of eigenvalue defines the stability. And also, if what about the magnitude of eigenvalue? If the magnitude is high, from this equation, let's see this equation again, Vi equals 1 by lambda I into Qi. If lambda I is very high, this means that for small variations in Qi, we have big variations in Vi, right? But if lambda I is, the magnitude of lambda I is large, then for small variations in Qi, we have small variations in Vi. So which is better? If lambda I is small, the sensitivity is more, so the stability margin is less. It's more, it's nearer to the unstable point. It's nearer to the unstable point. So that is about the magnitude of lambda I, and the sign of lambda I basically defines the region itself, whether it is stable or unstable. Now we'll see this again. Suppose lambda I is positive, it's stable. Lambda I is 0, it's unstable. Then lambda I is negative, it's unstable again. The magnitude of each modal voltage variation equals the inverse of lambda I. This is 1 by lambda I, right? Variation equals the inverse of lambda I times the magnitude of the modal reactive power variations. Modal reactive power variations here. 1 by lambda I into Qi. This is the modal reactive power variations. Okay. Now, the smaller the positive lambda I, the closer the ith modal voltage to instability. That means the machine is the voltage unstable point is nearer. Okay, we have already seen the sensitivity, the extent of sensitivity. Okay, we have commented on that. Then when lambda I equals 0, the ith modal voltage collapses because any change in the modal reactive power causes infinite change in the modal voltage. The same points which we have discussed, it is written here. That's all. So that is what is with the QV sensitivity and VQ sensitivity and QV model analysis. And from this QV model analysis, we'll do a problem in the next lecture. A numerical example we'll do. Thank you.